So, in the previous class we started this theorem. It is a very famous theorem in computer science due to Nisan and Wigderson. It shows that if there is an explicit function f which is average case hard, then you can use that to stretch a seed and get a pseudo random string. Okay, so basically you can use average case hardness to get a PRG. So, Sn hardness will give you S prime L PRG. So, this will prove in many steps, it will be a long proof. First, so the idea of this is that you use the average case hard function f on a design. Design means that you take a seed string is z, and on substrings of z you evaluate f, and these bits become your output. Okay, this is the stretched seed. So, first we have to show that this design exists. That was lemma 1, which we have shown by a greedy analysis. Second thing we have to show is that if this string based on design and f, if this string is not pseudo random, then f will be easy, average case easy. Okay. We have to show that. We basically have, what we will do, the idea there is that we will construct a bit predictor. So, that is lemma 2. Here we want to show that using the design and f, this Nisan-Wigderson I comma f image on UL, this is pseudo random, and the idea here is that if it is not, then there will be a distinguisher circuit C which we can use to predict bits, and hence f will become easy, which is a contradiction. So, that is the idea. We want to construct a bit predictor circuit C prime, and that will contradict the average case hardness of f. So, how do you construct C prime from C is the next question. So, let S be the average case hardness of f, and suppose this circuit C is the distinguisher, it is small size S by 10, and it is able to distinguish between this Nisan-Wigderson I comma f on UL distribution from the C of UM distribution, from NW distribution on UL to UM. Okay, that is what. Remember, stretch is from L to M, that is the stretch following the design. So, this difference in the probability is more than 0.1, let us assume, and without loss of generality we can assume that it's the difference is positive. So, the probability difference is at least 0.1, and let us now devise a bit predictor. So, the way we will create the bit predictor is we will try to first locate the place where the bit prediction can happen. Okay, so, NWUL has m bits, it is an m bit string. We first have to identify the location where the prediction can happen. Identify the bit which can be predicted. So, let us first do that. So, define distributions D0 to DM such that for all I, this distribution DI will basically use only the prefix of NW distribution. Okay, instead of using the whole output of NW, you just use the first I bits, and the remaining part you choose randomly. That is the idea. So, DI is First choose x from the distribution UL, so 0 1 to the L, and Zi plus 1 to Zm are bits. Compute y, that's the NWIF string. So this will use the design I and the average case Hart function f, right? It will give you m bits. Only look at the first I bits. That is the new stretched string. Instead of y1 to ym, you just output y1 to yi, and the suffix is randomly chosen m minus I bits, zi plus 1 to zm. So this distribution we'll call di, and now you can look at the whole the spread. So d0 to dm, these distributions, right? d0 is all the bits will be random, d1 is first is y1, the remaining bits are purely random, and dm will be all the bits are y1 to ym, right? That's the whole spread of these distributions di that we have defined. This is called hybrid distribution. So you can observe that d0 is the uniform distribution, and as I said, dm will be your Nisan-Wigderson NW. So let us look at the way C behaves on these distributions. So the probability of C on di being 1. Remember, C is this distinguisher circuit that we have assumed. So probability of it on di is pi, and what you know is that Pm minus P0 is greater than equal to 0.1, right? Because Pm is the Nisan-Wigderson, corresponds to NW distribution, P0 corresponds to the UM distribution. So the difference of C on these two, probability difference, is large, it's 0.1. So from that you can deduce that there is an I0 such that Pi0 minus 1 is 0.1 by m, right? This you get by averaging. Because if for all I0s these differences are small, then the difference between Pm and P0 will also be smaller than 0.1. That cannot happen. So somewhere it has to be larger than this average 0.1 by m. So that now kind of gives me the location I0. Okay, this is the bit where there seems to be some probability difference which is large. So I think that this is the location, this is the bit that's predictable. So how do you predict it? So you predict it by basically by evaluating C. Okay, if you get 1, then maybe you say you output some value for the bit, otherwise you output the opposite. So we will now work this out. So we intend to use this advantage to predict the I0th bit of NW IFUL given the preceding ones. So if you are given everything till I0 minus 1, then the I0th one we will try to predict using this probability difference, and obviously using the circuit C that is given to us. So let's define that predictor. So on input y1 to yi0 minus 1, pick zi0 to zim randomly, random bits. So now you have m bits, prefix is y's, suffix is z's, and just see whether what C evaluates to on this. If it evaluates to 1, then you will output zi0. If it does not output 1, then you will negate zi0. That is the idea of prediction. So essentially C prime is just guessing the I0th bit by randomly picking it and evaluating C. So zi0 if C on these y's and z suffix evaluates to 1. Why are we outputting zi0 when C evaluates to 1? Well, because you know that C evaluating to 1 is higher than, there is this difference in the probability, right? Pi0 is sufficiently bigger than Pi0 minus 1. So and Pi0 was the probability of distribution Di0, right? Remember, in Di0 you are using the first I0 bits from the NW generator. So if you use NW generator based prefix, then there is a higher chance of C outputting 1. So hence, I mean, intuitively it makes sense to, whenever C evaluates to 1, in this situation, whenever you see with this prefix C is evaluating to 1, then there is a better chance of Zi0 being the correct answer. Okay, so we have to actually compute this probability, but this is the insight behind the definition of C prime. Otherwise, you just negate Zi0. So obviously the question is, how well does C prime predict? yi0, right? What is the success probability? So this will be kind of Bayesian probability analysis. So let's do that. So the probability of C prime on y1 to C prime given y1 to yi0 minus 1 predicting yi0, where y refers to the NW output and Z refers to UM. So this probability, right, Y's are picked from the prefix of NW and Z's are picked from the suffix of UM. That is what we mean by this notation. So this is equal to, let's write down two cases. So first is Zi0 being equal to yi0, which means that Zi0 was the correct value. So what is the probability of C prime being yi0 in that case, right? So in that case, basically C has to evaluate to 1. Plus probability that Zi0 is not yi0. So in this case, C prime will output yi0 only when C evaluates to 0. So let's write that. Okay, so this is equal to, so Zi0 is randomly chosen, so this probability is half times the second probability is, that is just the probability of di0 minus 1. So probability of C on di0 minus 1 being 1, that's what it is, plus another half times, now this is probability of C not being 1, so which will be 1 minus probability of C being 1 on what? On yi0 complement. And remaining is Zi0 plus 1 dot dot Zim equal to 1. Okay, so let us further simplify this. So first is, so I'll get half plus pi0. So I'll rewrite it like this: pi0 and I have to subtract. This was not di0 minus 1, this is di0. This is how we define the distribution. So in di we take Zi plus 1, yeah, this should be minus 1, and this is pi0 minus 1, plus I'll put the half, then I'll subtract half, and what else do I have? I have minus half times this probability expression. What is this probability expression? So let me in fact club these two together. So I'll get plus the probability of C y1 to yi0 minus 1 I0 bar ZIM being equal to 1. Okay, so now what is this thing inside the bracket? Pi0 minus 1 plus this probability of C with yi0 negated. This is di0 because zi0 is actually yi0. So, we are using up to i0 prefix. So, that is by definition di0. So, if you look at this, so this is the probability of C with y1 to yi0 minus 1 yi0 and then z's. Okay, so what you see is probability of C being 1 plus a similar expression. The only difference is first has y0, the second has yi0 complement, right. So, this probability sum will correspond to the distribution I0 minus 1. Okay, so, up to I0 minus 1 you are actually using the prefix and the remaining things you are taking random. So, in other words, what you can write is this. This is equal to Pi0 plus half minus half, and here you will have Pi0 minus 1 times 2, because Pi0 minus 1 is essentially prefix up to I0 minus 1, and the I0th one with probability half you choose 0 or 1, right. So, that is what the sum of the probability is, the average of that. So, which is why this 2. Okay. So, this gives you half plus Pi0 minus Pi0 minus 1. Right, and that is a big advantage, because you know that Pi0 minus Pi0 minus 1 is a probability, this probability difference is at least 0.1 by m. So, you get this much of advantage. Right. So, C prime is actually better than just a random output. It is actually making a significant improvement over half. So, that is why we can say that C prime is a bit predictor. So, this implies that C prime is a decent bit predictor. The only issue is C prime is using these random bits ZI0 to ZIM. So, we have to make it somehow go away, we have to make it deterministic. What you can do is you can actually just fix these bits ZI0 to ZIM suitably, so that the advantage is not lost. So, to make C prime deterministic, fix ZI0 to ZIM suitably. And get circuit C prime prime. So, C prime prime will continue to have the advantage in prediction. where y is coming from the Nisan-Wigderson stretch. Okay, so now there are no random bits being used because the remaining z is fixed to a good choice, and so there will always be some good choice of fixing z, right? Again by the averaging argument. So based on the averaging argument, we have fixed z suitably. So now they are gone, and we have that C prime prime just takes I0 minus 1 prefix of NW image bit with a good advantage. The advantage is 0.1 by m. Now, what is the size of C prime prime? Size of C prime prime is the same as the size of C, right? Why is that? Because it's basically just using C. It evaluates C and then either it will output Zi0 or the complement. So it is just an OR. So the size is at most twice that of size of C, kind of if then else, which is then less than equal to S over 5, because C was size S by 10. So plugging the definition of NWIF, we get the following, that the probability of C prime prime, what are these y's, right? Y's are just evaluations of f on the substring of seed Z using the design. And using I0 minus 1 evaluations, you are, or C prime prime is predicting f on I0th substring with an advantage of 0.1 by m. That is what C prime prime is doing. So now the question is, how do you deduce that f is easy from this? Right, this seems to be taking values of f and giving another value of f. So somehow we have to remove f from the argument of C prime prime, and the way we will do it is by fixing many of these z's. We will fix many of the z's. So let us fix z other than I0, right? On the RHS you have I0, so other than I0, that part of z you should fix, and then in the left hand side hopefully you will remove the extra z's, and you can then maybe say that f at Zi0 is being evaluated on the left hand side. Okay, that's the idea. So let's fix L minus I0 substring such that the above probability is retained. So this means that for j I0 minus 1 to I0 minus 1 Zij has all places fixed except Ij intersection everything other than I0 is fixed, right. So, ij intersection I0 is what remains. And what can you say about ij intersection I0? So, ij intersection I0, we have to go back to the design, right. We had a design that we were using in NW definition. So, in the design we said that intersections are smaller than D or at most D. So, that is what happens here. So, by the way, this I have to correct, this is not I0, this is at I0 and this is at I0. So, ij intersection I0 is small, that is less than equal to D. So, this means that f Zij in this, how many arguments are actually free at most D? So, this is D variate. Okay, so, by this fixing in the left hand side, these all these Zi1 to Zi0 minus 1, they will all become just D variate. D is considered small. So, now we will do a trick of also eliminating them. So, this f is a hard function, right. Remember that we started with an average case hard function. So, in the left hand side, our goal is to actually make these fzi1 etc. easy to evaluate, so that we can claim that left hand side is easy, right hand side is hard, but still we are able to get an equality. Now that will happen because f on this Zij after the fixing has become only D variate. So, since it is only on D arguments, you can evaluate it in circuit size 2 raised to D. So, this means that f Zi1 to f I0 minus 1, these functions, since they are on few variables after the fixing, they can be computed trivially by circuits of size 2 raised to D. 2 raised to D is the number of inputs that you are giving to this f, and the size of the circuit will be D times 2 raised to D. Basically, there are these D variables and then they take 2 raised to D many values. So, you get this much sized Boolean circuit, which means that there exists a circuit B of size. Now, let us look at the whole thing which was on the left hand side, right. C prime prime on the arguments f on I1 dot dot f on I0 minus 1. So, this whole thing, what is the circuit size of this? So, this we will see as a circuit B, and you can estimate the size as C prime prime has size s by 5, then each evaluation of f we have written trivially as d times 2 raised to d, and I0 is at most m. So, that is the size estimate, which is equal to s by 5 plus what is m? M comes from the design. So, if you go back to the design, you will see that m is around 2 raised to d by 10. That is the estimate, right? And you can see that this is all less than s. This again will come from the value that s. In lemma 2, we assume that the average case hardness of f is more than 2 raised to 2d. That is what we had assumed, right? So, because of that, so clearly 2 raised to 2d is much more than this overhead that you are getting of 2 raised to d times 2 raised to d by 10, and even if you add s by 5 to that, you will remain under s. So, point being that B is a circuit of size quite small. Okay, so, in that sense, now you are getting that f is not hard at all. And what is the, how good is B computing f? So, the probability of B on Z I0 being equal to f at Z I0 on the inputs Z I0. How big is this set I? This is an n sized subset, right. So, on this domain of UN, B evaluates f with advantage 0.1 by m, which is more than half plus 1 by s, right, because s is greater than m. M is around 2 raised to d by 10, s is more than 2 raised to 2d. So, the advantage is more than 1 over s. So, it seems that f is being evaluated by B pretty well, okay, and that is a contradiction, because we had assumed that f is average case hard. So, this contradicts. So, B contradicts the assumption that average case hardness of f is s, because B is a circuit of size smaller than s, and it is able to compute f on more than half, sufficiently away from half, many inputs. So, what does this give you in the end? So, this contradiction ultimately implies that what we had assumed, NW's output being not pseudo random, it actually is. So, we deduce that NWIF on UL is S by 10 0.1 pseudo random. Okay, so, this finishes the proof of lemma 2. So, we have shown that lemma 1 showed that there is a design. Lemma 1 showed that there is a design easy to compute. Lemma 2 showed that using the design and the average case hard function, you have a pseudo random distribution given by NW map. So now using these two lemmas, it's actually quite easy to prove the main theorem of Nisan-Wigderson. Okay, you just have to do some parameter chasing. So let us do that. So let f be in E, which recall is 2 raised to n time, and average case hard. Let us say the hardness is at least S of n function. So define a stretch function S prime L PRG, which it will stretch L bits to M bits using the design, basically this NW map. So on input Z 0 1 to the L, what you do is pick n such that basically you want n, I would say something like square root L. To have a design you need L and D of a certain type. So you want L to be slightly quadratic, around quadratic of n. Okay, so pick an n like that. So don't worry about these parameters. So take it to be this. So L is basically, you can think of it as n square, it's quadratically related. Now there is a design, L and D design, use that. So compute an L and D design I M you can take to be 2 raised to D by 10. So this L and D design is just a set of or family of sets. These are 2 raised to D by 10. Their mutual intersections are small, smaller than at most D. Each of them is an n subset of 1 to L, right? Remember that is the design. You can compute it in time 2 raised to D. So it's very explicit, and using this you can stretch Z. So output this NW stretch. This will stretch L to M, and in how much time? This takes time 2 raised to L plus, basically just we have already seen the design, so that is okay. It's just that you have to also look at what NW does, right? NW is it's just evaluating F. on n bits. So that you can do in 2 raised to n time. Times and this you have to do m times. So overall this is still 2 raised to L. So let me just mention that this is for computing f. For computing f by the truth table, you can compute in 2 raised to n times. So we are using that, and 2 raised to L is for the design. So n is obviously smaller than L, and m is just something like 2 raised to d. So you still get 2 raised to L. So it's fast. We can say it's explicit. Now since the average case hardness of f is at least S of n, and S of n is, by choice, it is 2 raised to 10d. So then we can use lemma 2, right? Lemma 2 said that average case hard function and design you can use. Also you can note that the parameters I have chosen, L and D design exists by lemma 1. Okay, so you just wanted L to be more than 10n square by D, and that is happening here. L is more than 10n square by D, right? So this is by lemma 2. The design is by lemma 1. So design exists, and then NW is computed in this much time, and using average case hardness assumption you get that NWIF UL is Sn by 10, 0.1 pseudo random. Okay, so we have a pseudo random distribution, and we have a PRG, which is this NW map. It is stretching L to M. How much is the stretch? The stretch is 2 raised to D by 10, which is again Sn to the 1 by 100. Okay, so for hardness S of average case hardness S of n, the stretch that your PRG is giving is Sn to the 0.01. Okay, so it is not stretch is not S of n, but it is slightly smaller, and this function we can call S prime. Remember, L is like quadratic in n. So L is being stretched to S prime L, which is actually S of n to the 0.01. So Sn has to be sufficiently large for this to give something interesting. So this implies that G is an S prime L PRG. Note that in the definition of PRG we had this S prime L cube circuit, right? So you have to you should observe that S prime L cube is smaller than Sn by 10. and since we have shown that NW image is Sn by 10, you do get that it is an S prime L PRG. So, that finishes the proof. This stretch is interesting only when S prime L is Sn to the 0.01 this should be bigger than, and L is around n square, right. So, you want this to be larger than n square. So, you want Sn to be sufficiently bigger than n to the 200. So, basically the point is that average case hardness should be something like n raised to 200 or more for this theorem to be interesting, because in that case only the stretch is actually bigger than L. Okay, that it will make sense only in that case. And surely super poly hard thus super poly hardness of F gives a good stretch. Okay, so we have proved this very important theorem that average case hardness sufficiently high gives you a PRG. Okay, and it will be a good stretch if you are working with a super poly hard Boolean function. So, we can say that hardness implies PRG. Now, is there a converse to this? Hardness, in fact, this average case hardness implies PRG existence, explicit PRG. Does explicit PRG imply, or this PRG implies hardness for an explicit function? That also is true, not a very stunning connection, but just to understand the definitions you can do this exercise. So, you can show that if you have an SL PRG, then there is a Boolean function in E such that the worst case hardness is cubic. Okay, so you will not get a very stunning connection, but it is kind of this super cubic hardness of an explicit function is what you get. This really follows from the definition. So, let G be PNSL PRG. So n is SL and that is bigger than L. Now what do you think is this function Fn that is a candidate for hardness? It has to be related to G, to the PRG, right? So why not just look at the image of G and those strings you call the yes strings in the space and the remaining strings you call no. Okay, that defines a Boolean function Fn. So define Fn on 0 1 to the n. Fn is 1 if and only if x is in the image of G. Now since G is a PRG, it is computable in E, so Fn is also computable in E. It is a Boolean function computable in E. Yeah, let me call this F. So let Cn be the smallest circuit computing Fn. So what is the circuit size? What is the size of Cn? That's the question, right? So the thing is that what you can show is that immediately you get that Cn on the image of G, right? It has to be 1 all the time, and on the other hand, what is Cn on Un? How frequently is it 1? Now recall that the image of G has only 2 raised to L strings, right? So you can estimate this as 2 raised to L by 2 raised to N, which is definitely smaller than half. So Cn on Un is less than half times, many times 1, while Cn on the image of G is always 1. So Cn is able to distinguish the two distributions. So Cn distinguishes GUL from the uniform distribution Un very well. So which means that by the definition of PRG, that size of Cn has to be more than the stretch cube. And what is the stretch? S of L is N. So what you have shown is that the complexity of this Boolean function f is at least cubic. That is the lower bound. Okay. So this is not highly interesting, it just follows from the definition that PRG implies some hardness, but hardness connection to PRG is much more impressive.